Now let's continue to discuss power series. And to remind you, so a power series and without loss of generality in this section, I'm going to talk about power series centered at zero, but anything what I'm going to say can be easily shown for series that are centered at a generic point A. So a power series for centered at x equal to 0 is anything that looks like a sum, say n from 0 to infinity, an times x to the power n. This is the power series, the sum of the power series, if the series converges, will depend on x. So a power series generically is going to define a function f of x. The domain of this function, as we have shown, is its interval of convergence. And the intervals of literal convergence I can find by using either ratio or a root test. We discussed that the root test is a weaker notion. So generally, if a root test gives you a prediction, then that means that the ratio test will give the same prediction. So this can be determined by the root test. And what we will do in this case, again, as you remember, we need to take lim sup as n goes to infinity of absolute value of an x to the power n raised to the power 1 over n. So this is going to be lim sup n goes to infinity absolute value of an to the power 1 over n times absolute value of x. And x, of course, is a fixed constant. Everything is positive here. So I can pull absolute value of x outside of the limit sign to get absolute value of x times lim sup n goes to infinity absolute value of an to the power 1 over n. And what I'm requesting from this for my series to converge, I want the outcome to be less than 1. And so therefore, if I solve this for absolute value of x, you're going to get two choices, or three choices rather. First of all, absolute value of x should be less than 1 over lim sup n goes to infinity of an to the power 1 over n, right, if I solve this inequality. And that is if this limit is finite. you're going to get 0. So x is only equal to 0 if the same limit is equal to infinity. And x is less than, absolute value of x is less than infinity if the limit is equal to 0, right? This is a theorem that we proved before. And so we have these three cases. And then the quantity 1 over lim sup basically represents the radius of convergence, and the interval of convergence is you go from 0 by minus radius of convergence to the left by radius of convergence to the right, and that gives you the interval of convergence. So, right. So then we can say, let me just write this down. R equal to 1 over this guy is going to be exactly the interval of convergence, the radius of convergence. All right. Okay, so if this is a case, then we know what the interval of convergence of a given power series is. The next question that we asked was this: is or where is the power series continuous? So where in its domain is the power series continuous? So we already know, right, that the power series is going to be continuous on an interval of convergence, is going to be defined, right? Is going to converge on an interval of convergence, but whether or not it is continuous, we don't know. And to determine if the power series is continuous or not, right, we need to test the series for uniform convergence. And we have done that before. And what did we do? We used basically the Weierstrass M-test, right? And in this case, what we did was the following. So I'm going to fix any R1 in the interval from 0 to R. So R again is the radius of convergence. Okay, so if I do that, so then clearly the series n from 0 to infinity of an x to the power n, that series converges at R1, right? Because R1 is within the interval of convergence. So in fact, I can just write an R1 to the n. So this guy converges. And in fact, because a root test is going to test for checks for absolute convergence, then we conclude from this that actually the sum of absolute values of an r1 to the power n, that also converges, right? R1 is already positive, so absolute value of an r1 to the n is a convergent series. All right. Well, not only that, but also, of course, if I compare some in fact, if I do this, if I compare absolute value of xn, of an times x to the power n, right? If I compare absolute value of this with absolute value of an times r1 to the power n, when let's see, when x is between minus r1 and r1, in fact, I'm going to include minus r1 and r1. So if x is between these two values, then clearly I have less or equivalent sign here. And so what have I got? I've got that absolute value of the terms of my series is going to be smaller than the entries of, or the elements of a regular series that converges, and a regular series which consists of positive, which is a sum of positive numbers. And then immediately, Weierstrass m-test tells me that the sum from 0 to infinity of an x to the power n, that this converges uniformly on the interval from minus r1 to r1, right? And because partial sums of the power series are always continuous, are continuous, we conclude that sum from 0 to infinity of an x to the power n is continuous on minus r1, r1. Right, before we did this for particular examples of power series, but you see that this actually is a statement that holds for all power series. And then finally, from this, we conclude that because R1 is arbitrary, well, R1 is not completely arbitrary, R1 is between 0 and R, because this thing was chosen arbitrarily, by sending R1 to R, the series is actually going to be continuous on the entire interval on minus RR. Okay, and so the conclusion from this computation is as follows, that a power series is continuous on its interval of convergence. All right, so this is good. So that means that if I take any power series, as soon as I found its interval of convergence, I can guarantee that the sum of a power series is going to be a continuous function on that interval of convergence. In fact, we will probably prove this later on, as I skip this section for now. One can show that the power series is not only continuous, but it's also differentiable. On the same interval from minus R to R, and the derivative of a power series can be taken in a way that you would expect. So what is a power series? Power series is an infinite sum of terms that look like an x to the power n, right? So in a sense, this is actually a polynomial. And if of a polynomial, you take term by term. So it turns out that this is true for infinite series as well, infinite power series on their interval of convergence. But this is a sum from 0 to infinity, and you take a derivative term by term, and you get n times an x to the n minus 1. And notice also when n is equal to 0, then this factor is 0. So this is also the same thing as a summation that starts from 1 and goes to infinity of n x to the n minus 1, which should make sense because the first term of a power series, a0, is just a constant. It doesn't have any x's in it. So when you take its derivative, it is going to disappear. Okay. But furthermore, if I can spell furthermore. If I look at the expression for the derivative, then that expression is itself a power series. With different coefficients than the original series, but still a power series. And so therefore, this thing is also differentiable. And you can apply the same formula as in the previous line here, right? So you take a derivative twice, you get n minus 1 down. X to the n minus 2 is a power, and so on. So another conclusion that we're drawing from this then is that a power series, right, nothing says that I can stop, that I should stop at a second derivative, right? I take a first derivative, it's a power series, I took its derivative, it is a power series, so it must be differentiable. I take a derivative again and again and again. And so that means that the power series is differentiable infinitely many times on its interval of convergence. Fine. Okay, so again, to summarize, a power series is going to be a continuous differentiable function, and not only it's differentiable, but it's differentiable infinitely many times. Everything on its interval of convergence. Well, now let's try to compute a few derivatives and see what we get. So let's consider f of x equal to a power series sum of an times x to the power n. Okay, so then from here I can see that f of 0 is going to be what? In the series, all terms have x to the power, x to some power in it, except for this first term, right? When I use n equal to 0, then I have x to the 0, it's just a constant. So if I plug in x equal to 0, then all terms will vanish, except for the first one, which doesn't have x in it, and that first term is simply a0. Okay, that's fine. So then what about f prime of x? We just written the formula for that. That's a sum from 1 to infinity of n times an x to the n minus 1. Let's think here. So if n is different from 1, then n minus 1 is a positive integer. X to the positive integer is going to be 0 when x is equal to 0, right? So if I'm computing f prime of 0, what will happen? When n is larger than 2, I have x to some power, 0 to some power is 0, so those terms are gone. And the only term that survives is when n is equal to 1, because that one wouldn't have any x. You just have 1 times a1, so a1. We have a lot of time on our hands, so let's do more of these. What about f double prime of x? And remember, again, I can compute as many derivatives as I want, because my original function is going to be differentiable infinitely many times. So I take derivative again, term by term, so n minus 1 comes down. I still have an, and I have x to the power n minus 2. Well, so now if n is 1, or if n is 0, this product is 0. So that means that I can start from 2 because the first two terms will contribute nothing. And likewise, now if n is greater than 2, then I'm raising x to some power. And so if I make x equal 0, then the only term that would survive is the first term in the sum, which corresponds to n equal to 2. So 2 times 1 times a2 times x to the 0, right? So that's how I'm going to write this. 1 times 2, a2, and that's it. One more, f triple prime of x. So you probably already got the gist of it. So I take the derivative one more time, n minus 2 will come down. So I can start summation from n equal to 3. And then I have n times n minus 1 times n minus 2, an x to the n minus 3. Once again, plug in 0. Only the first term without x survives. That's a term with n being equal to 3. So if n is 3, then this is x to the 0. This will become a 3 times 2 times 1. So 1 times 2 times 3, a3. And now what is going to happen if I do this k times? So if I take kth derivative of f of x, what's that going to be? It's going to be a sum, right? For f prime, I'm starting from 1, double prime, I'm starting from 2, triple prime, starting from 3. So for kth derivative, I will have to start from k. So n from k to infinity. And then n times n minus 1 times etc. times. And what is the last entry here? It's going to be for 1, I don't have anything. For 2, it's 1. For 3, it's 2. So the last one for k is going to be n minus k plus 1, right? Times an times x to the n minus k. And let me shift this a bit. And so what am I going to get if I compute kth derivative evaluated at 0? Everything is going to be still gone except for the term with n equal to k. And if I look at the term with n equal to k, there should be a k that survives. And then here I'm going to start from k, then k minus 1, etc. And the last thing will correspond to n being equal to k. So k minus k plus 1 is 1. So this should be a product of all integers from 1 to n. And that is what we denote by, from 1 to k, that's what we denote by k factorial. And then there is ak. And so vice versa then, if I solve this equation for ak, I'm going to get that ak is equal to f kth evaluated at 0 divided by k factorial. And so from that, so this is for every k. And by the way, to this end, 0 factorial is understood to be equal to 1, and 0 of derivative is a function itself. All right. And so then I can write the series in equivalent way. that the function f of x, the sum of a series, is a sum from 0 to infinity. What's an? I have to substitute, replace k by n, so I'm going to get nth derivative of f evaluated at 0 divided by n factorial times x to the n. Right, so it is just a fact of life that we just now established for functions given by power series, that I can write a power series in this way, where I expressed all the coefficients of the power series as derivatives of a function which is a sum of the power series. Okay? All right, so that's good. So let's try to answer the following question then. Let's suppose that someone, let me insert the word power here. Someone given me the function f of x. So what about the following? Following example, actually. Let's take f of x that is equal to e to the power x. Okay. If I have a function that is e to the power x, the domain of this is all real numbers. And not only that, but if I take nth derivative of this function, then of course the derivative of exponential is itself. So this is e to the x for all n greater or equal than 0, right? Again, 0 of derivative is a function itself. Okay, fine, whatever. But then, of course, nothing prevents me from evaluating nth derivative of f at 0. So this should be e to the 0, and that is equal to 1. Okay, fine. And then if I have these infinitely many numbers, fn of 0, then nothing really prevents me from writing a series like this, right? So then from here, I can consider the series sum n from 0 to infinity fn of 0 over n factorial x to the power n. So in this case, fn of 0 is equal to 1. So this is nothing but sum from 0 to infinity of x to the n over n factorial, right? Because fn of 0 is equal to 1 for all x. Okay, so this is a power series. And we're going to, because this series was generated from the function e to the x, it's called the Taylor series. For e to the x. All right, so I have a function. From that function, I produced a power series by taking derivatives. Fine. So What's the radius of convergence of this function? I'll need to use my root test or a ratio test. In this case, because of presence of n factorial, a ratio test is probably better. So use the ratio test. When you take a limit n approaches infinity of absolute value x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. Only things that can be, well, in fact, before I do anything, x to the n plus 1 divided by x to the n cancels out, and I have only x left, and x is the only thing that can be negative in this case, so I have to replace x by its absolute value. So limit n approaches infinity, then absolute value of x. Then I have 1 over 1 over n factorial, so n factorial goes to the top, n plus 1 factorial goes to the bottom. Well, this is still a limit, n goes to infinity. N factorial is a product of all integers up to n, and n plus 1 factorial is a product of all integers up to n plus 1. So I can write it as n factorial times n plus 1. N factorial goes away. And then x is a fixed number, and I'm taking a limit when n goes to infinity, and in this case, so fixed number on the top, bottom goes to infinity. This is 0, less than 1. So then the radius of convergence of our series is infinity, and so the interval of convergence is the entire real line. Okay, so my exponential function that I chose to use in the beginning, it's a function which is defined on the entire real line, and I associate it with this, its Taylor series, so this power series where I took derivatives of e to the x and I stuffed them into the expression for the power series, and I got that. So that Taylor series apparently also has a radius of convergence, also has an interval of convergence which is entirely real line, because the radius of convergence is infinity. But what does f of x, or what does e to the x, have to do with the power series that I circled? Again, by default, nothing, because I just wrote some series. Well, but maybe on the other hand, if I have a power series, just a straightforward power series, that power series adds up to some function of x, then we discovered that for power series, this formula is going to be true. And now I'm trying to apply the same formula to a function of which I don't know if it can be written as a sum of the power series. So by default, it's not clear that e to the x should be equal to this. If e to the x was a power series, right, then of course two things are the same, e to the x and that would be the same, because that's how I got this formula. But if I don't know a priori that e to the x can be written as a power series, then as this power series, in fact, then I don't really know if this has anything to do with that. So question, is it true that e to the x is equal to the sum from 0 to infinity of x to the n over n factorial? Right? We don't know that. If we think that this is true, then we need to prove this. So if this is true. All right, so before we discuss how we can do that, let's actually look at a specific case of corresponding to this example. So for this particular function, let's observe a couple of things. That as a power series, this series, as we just discussed a few minutes ago, is a function that is differentiable on its interval of convergence infinitely many times. Okay? All right, so let's take a derivative. So compute the derivative. Sum from 0 to infinity, x to the n over n factorial. Again, how are we computing derivative of a series? We're taking derivative of each term in the series. So this would be sum, and from when I took derivative, right, I can start now adding things from n equal to 1, from 1 to infinity, and x to the n minus 1 divided by n factorial. Well, fine, but n over n factorial is a product of all integers up to n. So n factorial contains a factor of n. So I can cancel n, and the denominator becomes n minus 1 factorial. So this is a sum, n from 1 to infinity, x to the n minus 1 over n minus 1 factorial. All right, let's do this. Let's introduce a new index. Let me call it k equal to n minus 1. If k is n minus 1, then n is going to be k plus 1. And so if we move this a bit to the right, so if I replaced an index n with an index k is n minus 1, n starts from 1, k starts from 0. And of course, it still goes all the way up to infinity. Then I have x to the n minus 1, which is k, over n minus 1 factorial, which is k factorial. Okay, so but now k is a dummy index, right? It's an index which is internal to the sum once I added the elements, the sum is not going to depend on k. And in fact, I can denote, replace k by any other letter that I wish, right? It's not going to change anything. Well, in particular, I can change k to n. So then I get sum n from 0 to infinity, x to the n over n factorial. And what do we see? We see that if I take a derivative of this sum, I'm recovering exactly the same sum. So in this case, the derivative of a function is equal to a function itself. Now, if I repeat this again, then second derivative is also going to be equal to the same thing. So the conclusion then is that if I take any derivative let's say m times, I'm going to recover exactly the same function that I started with. So, and that is a thing that works strongly in favor of the fact that the sum of this series must be an exponential, because exponential function is only one that has this property that is equal to its own derivative. So this hints that sum from 0 to infinity of x to the n over n factorial is indeed equal to e to the x. But so far it doesn't prove it, right? Okay. So we need to come up with some sort of uniform way of proving when the function is going to be equal to the sum of a corresponding Taylor series. In other words, we need to figure out a way to answer a question like this: that if I have a function, whether or not this function is going to be equal to the sum of its Taylor series. And that question will be answered in a Taylor's theorem that we're going to discuss in the next lecture.